All right, this is one of the last topic in this section, looking at definite integrals, and it's, I think, my favorite one because it's examining work. And when we use this word work, what we're talking about is the physics application or definition. And for those of you that have studied physics, and if you haven't, shame on you, study physics. Uh, work equals force times change in position. And this is what you would have learned in a physics class if you if it were not using calculus. So the idea is, imagine there's a block and you're going to push this block with a force of 2 newtons. That's the measurement of force. And you're going to push it 2 meters. So the work done required to go from here to here, going 2 meters, is let's make that 3 meters, is the force times the change in x, which is 2 newtons times 3 meters. So we get 6 Newton meters. So the idea of work is that you're doing force over a distance. Well, what makes this interesting in terms of calculus is that we can now think about what happens when our force varies. So when our force is varying, so let's say that our force equals some function that depends on x, then, if we call this x equals 0 all the way to x equals 2, at any given point, let's call this delta x, my force at this point, so the work that's done to bring it from here to here is f of x dx. And if I made another cut, like right there, and called this dx, and at this point I've got some force, f of x, the work that's required to get me from here to here, that little bit of work, that little change in work, is f of x times dx. So having seen a bunch of definite integral problems, you should be able to make that leap that, well, it's written right here too, that work is the sum of all of these little d works, dw's. So work equals um, the integral from point A to B of my force function times that little dx. Let's look at an example. So we have a container moving along an assembly line. So, here's our assembly line. And it's being filled with merchandise. So when it gets heavier and heavier and heavier and harder to push, so when the container's at point X, the force needed to keep it moving is as follows: this many pounds. How much work is done in moving the container from 0 to 6 feet? Well, we could go right to the definite integral, but let's think about this in terms of a Riemann sum. So let's divide the integral into 3 equal subintervals. So we've got 0, 6, 2, 4. And let's assume the force is constant on each subinterval. So in other words, constant, constant, constant. And it's going to be obtained by using the value at the left-hand endpoint. So the force at 0 is just 4. And at 2, putting 2 in, 6. And at 4, putting 4 in, you're going to get 12. So over that first 2 meters, we're assuming that the force is 4 pounds the whole time, so the work would be 4 times the distance 2, plus, now we've got this from 2 to 4, we're assuming that the force is 6, so that work will be 6 times 2. And then we have to do the work from 4 to 6, assuming that the force is 12, so 12, my force, times my distance, 2. So these are all using the force times change in x. A change in x, and then the force. So I could approximate the work as being 8 plus 12 plus 24, which equals 44. And that's good, but the more subdivisions I do, the more accurate it's going to be. And so that brings up the idea of taking the integral. So the idea here with a definite integral is now we have a little infinitely small cut with dx, and the force at that point is 4 plus 1/2 x squared. So the work is going to be the force at that point times the little change in distance. And what we're going to do is add up all of these little works. So we're going to add up from x equals 0 to x equals 6, my force dx, which is 0 to 6, 4 plus 1/2 x squared dx. And here's my definite integral expression. We don't need to actually go through and evaluate that. Okay, so this problem, if you've never seen springs, might seem a little bit confusing, but springs are a really interesting thing to study in physics because they're the force that the spring is exerting, or that you need to exert on a spring, is proportional to its position. So the further the spring goes away from its natural position, so here it's at its natural position, and now we're moving the force. As we get further and further and further away, that force increases. You know, the spring has a more desire to pull back the further you go away from it. So to start off, it says, suppose that 10 pounds of force are required to stretch a large spring 4 inches. Well, we know here that the force required to stretch a spring x units beyond its natural length is proportional to x. And we want to show that if 10 pounds of force are required when you stretch it 4 inches, that this c value would be 30 pounds per feet. So the key thing is we need to talk about pounds and feet. So 4 inches is 1/3 foot. So therefore, you know, if we look at this equation, my force is 10 pounds, and that equals c times my x value, which is 1/3. So c equals 30. So that's physics for you. But now let's get into the calculus piece. It says to approximate the work done in stretching the spring from 0 to 2 feet, let's divide the interval into 4 equal subintervals. So 0 to 2 feet, 4 subintervals. And we want to assume that the force is constant on each subinterval. And again, we're going to use a left hand. Well, we've been using left hand. Let's use a right hand endpoint. So let's write a sum with 4 terms that approximates the work. So we need to find the force at the following 4 places since we're doing a right hand. And we now know that the force equals 30x. So we're going to have 15 and 30 and 45 and 60. So the idea being that on the first 0.5, so we're incrementing by 0.5, each of these increments is 0.5. So the amount of work done in that first increment would be 0.5, my distance, times 15, the force, plus over this distance of 0.5, my force is 30. And over this distance of 0.5, my force is 45. And over this distance, my force is 60. So each of those 4 terms represent the work done to move the block over that 0.5 foot interval. And if we add that up, that will approximate the work for us. However, there's a much better way of doing that. And of course, the better way that I'm talking about is using calculus. So because, well, I mean, this is calculus ideas. It was the foundation of calculus, the Riemann sums. But what we want to do is write and evaluate a definite integral to show the work done in stretching that same spring from 0 to 2 feet and show that it equals 60 feet. 60 foot-pounds. That's the measurement of the work. So again, the force required to move that spring from 0 to 2, the force equaled 30x. And at any little sliver, so if we call like some little sliver there, dx, the force is 30x. So the amount of work being done to move it that little distance dx is 30x dx. So we're just going to add up all of these little works, these d works, from 0 to 2. So we're going to add up from 0 to 2 all the little work that's being done. And if we go ahead and evaluate that, we get this equals 15x squared from 0 to 2, which equals 60 foot-pounds. All right, so a couple more problems. Hopefully you're picking up on these ideas. It says when a particle is located at a distance x feet from the origin. So what I'd like you to do is stop this video and try to get an answer for this. All right, so the force is varying. Here's how it's varying. And we want to know how much work is done in moving the particle from 1 to 3. So the idea is we think about having a little cut, and that has a distance dx, and we want to think about the work done in moving it that little distance. And the force at any point is x over 1 plus x squared. Well, what we're going to do is add up all of these little, the little work in this section would be the force times the distance. So we're going to add up from 1 to 3, x over 1 plus x squared dx. While I haven't been solving many of these integral problems, let's just do this for sake of review. We can add a 2 there and a 1/2 there. And we're doing that because now the top is the derivative of the bottom. So therefore, we're going to be using ln. So this equals 1/2 the ln of 1 plus x squared evaluated from 1 to 3. So 1/2 ln of 10 minus 1/2 ln of 2. And for anyone who wants to go above and beyond, this equals ln of root 5. All right, another work problem. Again, pause the video, see if you can get this on your own. All right, so force of 12 pounds is required to hold a spring stretch 4 inches. Oh, wait a second. We've already done that. Yeah, we already did that. or one like that. Okay, so here we go. This is the last problem, and this is a interesting problem. It says Tim and Tom are pushing identical blocks over distance x. Tim pushes with the following force from 0 to 5. Tom pushes with this force until he does as much work as Tim. How far does Tim push the block? How far does Tom push the block? So Tom is going from 0 to some distance d that we don't know. So the first thing that we need to find, I think you guessed it, is the work that Tim does, because Tom needs to do as much work as Tim. So the work that Tim does is going to be the integral from 0 to 5 of f dx. So 3x squared plus 1 dx. Well, what does that equal? This equals x cubed plus x from 0 to 5, which is 130. Okay, that's how much work Tim does. What about the work that Tom does? Well, the work that Tom does is the integral from 0 to some unknown distance, d, f dx, so 3x plus e to the point 1x dx. And this has to equal 130. So what do we do? Well, let's solve this this definite integral, and we're going to get 3 over 2 x squared plus e to the point 1 x over 0.1, and that's evaluated from 0 to d, and this has to equal 130. Well, finishing this up, what we'll do is we're going to get an equation for d. Plugging in, we get 3/2 d squared plus 10 e to the 0.1 d. This 10 comes from flipping that over. Minus, and then plugging 0 in, we get e to the 0, 10, which equals 130. Well, this value here is just 10, so we're left with 3/2 d squared plus 10 e to the 0.1 d equals 140. And I'm going to stop it right there, because at this point we can't solve that by hand, but we could just plug that into a calculator and use our intersection button to see where that equals. So just to show you what I'm talking about, get our calculator out. If you have an Inspire, you would just use the solve button using this calculator. Let me get this set up. Okay, so here's our graph of the left-hand side of the equation, which is Tom's work, and we're setting it equal to, well, this was Tom's work up here, and we set it equal to Tim's work. Solve this definite integral, and we evaluate it for d and 0, and now we have this equation here. And that equation, this is y1, this is y2, where they intersect right there will give me the value of d, the distance that Tom must push the block. So second calc, intersect, and we get that Tom needs to push it a distance of 8.8 meters or feet or whatever that distance is. So this is how much he needs to push it, 8.8. All right, so this is a lesson on work, And so I hope you're not too overwhelmed by the idea of work as a topic. You study it a lot in physics. For us, uh, it does show up on the AP exam. It shows up in lots of physics problems. It shows up in a lot of calculus problems, mostly because it's a great application and interdisciplinary work between both the physics and the calculus. Well, I enjoyed that. Hopefully, you're able to follow along. Thanks for watching.